Good morning, Algebra 1 students. Welcome back to Algebra 1 after a day off yesterday. Hopefully at this point you have already completed problem 13 in section 8.1.2. Again, reviewing this generic rectangle, algebra tiles, factoring sort of situation. So hopefully you have finished number 13. In fact, if you haven't finished number 13, which some of you probably haven't, I want you to pause the video right now and go do it. I'm serious. Pause the video right now and do number 13. If you're done with number 13, tell Mr. Partridge that you're done with number 13, and then you can come back and play the video again. I'll wait. Okay, now that we're all done with number 13, we get to move on to number 14. So number 14, as you can see here, hopefully on my screen, begins with it says to develop a method for factoring without algebra tiles. So that's going to be our goal today, is we're going to try to go from using algebra tiles and manipulating with algebra tiles to not needing to do that and just being able to factor quadratic expressions with generic rectangles. So the first thing they want us to do is one more time to use algebra tiles to try to factor a quadratic expression, okay? The expression's right here, 2x squared plus 5x plus 3. They want us to try to factor that. So I do still have up these algebra tiles here from our CPM textbook, online textbook. And you can see here they have 2x squareds, 5 x's, and 3 singles. Okay, so that's good. That's our goal. We want 2x squareds, 5 x's, and 3 individuals. And I'm going to try to arrange this into a perfect rectangle. Now, if you remember, one of the rules that we use to factor quadratic expressions with algebra tiles is we always put our x squareds in the bottom left corner, okay? So I put the x squareds here in the bottom left. There's 2x squareds right there. And now these x tiles are going to get evenly split. I shouldn't say evenly split. They're going to get split up, some along the side and some across the top of the x squared tiles, okay? It's like there might be one down there, there might be another one down there, there might be one there, might be one there, and there might be one there, okay? So as you can see in this arrangement that I have enough individual little spots there in my top right corner to put my 3 individual pieces. Okay, so I want you to notice something about this diagram I've created, this pile of tiles, this rectangle. The 2x squareds are in the bottom left corner, and the 3 individual pieces are in the top right corner. And those are always all together. The x squareds are always together in the bottom left. The individual pieces are always together in the top right. It is the 5 x's that I've had to split up from here and here across the top and the sides of the x squared. Okay, so top left and bottom right. So the x squareds are together, the individual numbers are together, and the x's have gotten split up into 2 different groups. Okay, so if I take this idea and I go back to this problem, and we're asked to write this this expression here as a product of dimensions. Okay, if I just click back across the bottom here, there's 1x squared, another x squared. So across the bottom, again, the dimension is x and another x, right? So it's x and another x, and then 1, 2, 3 across the bottom. And then up the side, it's an x from the x squared tile and a single from that x. So it's x and 1, and across the bottom, it's 2x and 3. So the answer to A here is x plus 1 up the side and 2x plus 3 across the bottom. Now, I should note that when I write those out as dimensions, it doesn't matter which one comes first, right? If it's x plus 1, then 2x plus 3, 2x plus 3, and x plus 1, it doesn't matter. So those are my dimensions that I got from my algebra tiles. Okay, but again, our goal today in this problem is to go from using algebra tiles to not needing them anymore. So if you look at letter B, it says to factor with the tiles like you did in part A, you need to determine how the tiles need to be arranged to form a rectangle. And now using a generic rectangle to factor requires something slightly different, although there are parallels that hopefully you can see. So Miguel has this expression, 3x squared plus 10x plus 8. So 3x squared plus 10x plus 8, that's what he's trying to factor right there. 3x squared plus 10x plus 8. Okay, so it says he knows that 3x squared and 8 go into the rectangle in the spots shown over here. Okay, this rectangle over here. So how did he know that? Well, it's just like we talked about with our rectangle here. The x squareds are together in the bottom left, and the single numbers are together in the top right. So that's what he did. Bottom left and top right. Okay, 3x squared in the bottom left, they're all together. The plus 8, the individual pieces, together in the top right. And what we have to figure out is what's going to go in these two spots to make the correct generic rectangle. Okay. Now, what we have to remember is our big key takeaway from yesterday. The thing that if you didn't get it yesterday, you're not going to get what we're doing today. So you got to go back to yesterday and chat with your teammates, ask somebody a question, because it's super important. What we know about a generic rectangle is that when we multiply across diagonally like this, okay, the bottom left to the top right, or the top left to the bottom right, when we multiply across like that, it has to equal the same thing, okay? So how am I going to figure out what to do with these 10 x's that Miguel has in his expression? They have to go here in these two boxes. It could be 5 and 5, it could be 6 and 4, it could be 8 and 2. I don't know, but I got to figure out how many x's go here, how many x's go there, okay? But they have to multiply those two numbers, however I split them up. They have to multiply to the same thing that 8 times 3 multiplies to, okay? So 3x squared times 8, if I multiply those together, okay, multiply those, I get 24x squareds. So I need two numbers now that multiply to be 24, but add together to be 10. Why do they have to add together to be 10? Because the 10x is what I'm trying to split up in my rectangle, okay? So I need 10x's, but I need to split them in a way that the two numbers will multiply to 24. And hopefully, relatively quickly, you can figure out that's got to be 6 and that's got to be 4. It really doesn't matter which way those go, by the way. You can flip-flop them. That's totally fine. 6 and 4 are the numbers I need, okay? So then the question becomes, how do we figure out what the dimensions are now? Okay, how do we figure out what the dimensions are? Because now I know what's in the box, but what are the dimensions, right? Because it wants me to write the area as a product. So again, parentheses is going to be my final product here. So the way that I do this is I look across my rows and columns. Okay, so I'm going to erase this arrow in the middle here. I don't need that anymore. Okay, and I'm going to look across my rows and columns. So this row has a 6x and an 8. 6x and 8 can both be divided by 2. Okay, 6 can be divided by 2 and 8 can be divided by 2. Nothing bigger than that. All right, so that is going to be that part of my dimension. Okay, so it would be 2 individual pieces here. It'd be like a 1 and then another 1. It'd be 2 right there. All right. Now, if I do that across this row, the bottom row here, I have a 3 and a 4. Do 3 and 4 have any numbers they can both be divided by? Well, 3 can only be divided by 3 or 1. So that answer is no. I can't divide those by the same thing. So I'll just put a 1 because any number can be divided by 1. But they do both have the letter X. Do you see how both of those boxes have an X in them? That's great. So now I can do this. I can put 1x, right? So now the dimension up the side, you can see it right here. It's 1x plus 2, okay? 1x plus 2 is up here. And now I can do the same thing across the bottom by just looking at my columns instead of at my rows, okay? So looking at the left-hand column, going up and down, I have a 6x and a 3x squared. My numbers are 6 and 3, which can both be divided by 3. Okay, 6 and 3 can both be divided by 3. That's the greatest common factor of the two. And then they both have an x. Okay, so they both have x in that box, so I can take out an x, right? So that's what's going to start here. It's going to be 3x's, 1, 2, 3. Okay, you can kind of imagine like there's like 1, 2, 3 across the bottom there. Okay, and then this column, I have an 8 and I have a 4x. Again, my numbers 8 and 4 can both be divided very nicely by 4, and the 8 doesn't have an x, so that is my dimension across the bottom. 3x, and then 1, 2, 3, 4, because both of those can be divided by 4. So this is 3x plus 4. Okay, so the answer to part B is right there. 1x plus 2 times 3x plus 4. Now, just to recap what I just did there, again, it started with this process of recognizing I have 10 x's, and I needed to figure out what goes in those two boxes that will multiply to be the same thing that multiplied to 24 from the other two boxes. Okay, so again, that cross multiplication thing you discovered yesterday, super, super important. And then once you have the box filled in, it's about what can you divide out of this row, out of this row, out of this column, out of this column. Okay, and that will give you your two factors. It'll give you your base and your height. And no algebra tiles are necessary. You don't have to draw every single individual tile or anything like that. So the next part C here, says that Kelly, she's hoping to figure out a shortcut. So she has this expression, okay, 2x squared plus 7x plus 6. She knows, again, that the 2x squared and the 6 go into the rectangle, bottom left, top right. She also knows Casey's patterns for diagonals. That was yesterday's stuff. Without actually factoring yet, what do you know about the missing two parts of the generic rectangle? What do we know about this and that? Well, we know that when we multiply them together, they have to equal 12. Why 12? Well, because 6 times 2, right, going this way, 6 times 2 is equal to 12. 6 times 2x squared, that's 12x squared. 12x squared. So these have to multiply to be 12x squared. That would be the answer to letter C. Then letter D says to complete Kelly's generic rectangle, you need two numbers that multiply to be 12x squared. They have a product of 12x squared and they add up or have a sum of 7x. Where does the 7x come from? Remind yourself, where does the 7x come from? Oh yeah, it comes from up here because that's how many x's she had in her original quadratic expression. Okay, so now they want us to use a diamond problem, which we've been doing for a long, long time. Remember that our idea here is on the top box, we do x times y. The bottom box, we do x plus y. So we know that on the bottom, we need them to add up to be 7x. On the top, we know we need them to multiply to be 12x squared. So that means both of these are going to have x's, of course, right, to multiply to be x squared. The real question is what numbers multiply to 7, add to 7 and multiply to 12? What two numbers multiply to 12 and add to 7? Well, you can start by just thinking of what numbers add to 7, see if they multiply to 12. 1 plus 6, 1 times 6 is 6. 2 and 5, 2 times 5 is 10. 3 plus 4 is 7. 3 times 4 is 12. Ah, there's the ones I want, right? So in my diamond problem, I would have 3x and 4x, okay? So that 3x and 4x are also going to fill in my generic rectangle, which I'm going to draw a little bit bigger here. And then we'll do part E to finish this problem up. So 2x squared and 6 come from the beginning and the end of her original expression. We know that x squareds are always in the bottom left. The individual numbers are top right. And then my diamond problem tells me where do my x's go, right? How do I split those x's, 7x's up in the rest of the other two boxes? 3x goes there, 4x goes there. And now I'm ready to find my factors. How do I find the factors? Well, that's about across the rows and down the columns. So 3x and 6 are in the top row. Those can both be divided by 3. 2x squared and 4x can both be divided by 2, and both of those boxes have x. And then going down the columns, down and down, 3x and 2x squared. 3 and 2 don't have any common factors. The only thing you can divide those by is 1, but they do have an x. And then 6 and 4 can both be divided by 2. Okay, so there's my factors. 2x plus 3 is up the side, and 1x plus 2 is across the bottom. Okay, so that's all of problem 14. Hopefully you've been copying that down in your notebook with me. The rest of your day today is going to be a little bit more practice of that, a little bit more investigation of that. And we'll do more practice on this next week and on Friday as well. So if you have questions, feel free to reach out, ask Mr. Partridge, or send me an email, or we will certainly discuss it when I get back next week. So hopefully you guys have an excellent rest of your Wednesday, and we'll see you soon.